This interactive presentation allows you to explore content at your own pace. There are 5 main sections with multiple slides in each section. To check your progress at any time, click on the Module Overview button. This navigation pane can be accessed from most of the slides. This module is one of 8 in a Drainage Water Management Distance Education program. Other modules include Background on Drainage and Water Quality, Drainage Concepts and Tools, Drainage Water Management Planning Process, Water Control Structures, Drainage Water Management Layouts, New and Retrofits, Drainage Water Management Operation and Management, and related conservation drainage practices. The conditions under which the practice of drainage water management applies are outlined in national and state level practice standards. The practice is applicable to agricultural lands with surface or subsurface agricultural drainage systems that are adapted to allow management of drainage discharges. It may not apply where saline or sodic soil conditions require special considerations. Nor does the practice apply to the management of irrigation water supplied through a subsurface drainage system. In the Midwest, drainage water management is primarily used for reducing nitrate transport from subsurface drainage systems. However, the practice standard identifies 5 purposes for which the practice may be used. These include reducing nutrient, pathogen, and/or pesticide loading from drainage systems, improving productivity, health, and vigor of plants, reducing oxidation of organic matter in soils, reducing wind erosion or particulate matter emissions, and providing seasonal wildlife habitat. In addition to its use to reduce nitrogen, phosphorus, and pesticide loading from tile-drained cropland, drainage water management is also used to reduce nutrient and pathogen transport during land application of manure. For this application, the drain outlet is raised prior to and during liquid manure applications to prevent direct leakage of manure into drainage pipes through soil macropores. The practice may be used to potentially increase soil water storage during growing season. This increased storage may lead to improved productivity, health, and vigor. Crops are particularly susceptible to water stress around the time of reproductive growth. Any extra water available then could result in significant yield increases. Drainage water management may be combined with sub-irrigation to maintain set water table levels. However, the practice only involves the setting of outlet levels for the associated drainage systems. Yield benefits, therefore, are dependent on rainfall patterns and may be inconsistent. The practice may be used to retain soil water, thereby reducing aerobic conditions and consequently the oxidation of organic matter, which leads to loss of productivity in mineral soils and subsidence in organic soils. In organic soils, however, high water tables may restrict root growth and limit the availability of nutrients. Therefore, these systems need to be aggressively managed. Excessively dry soil is susceptible to erosion by wind. Drainage water management structures can be used to retain soil moisture, thereby reducing surface dryness, creating a surface more resistant to wind erosion. Before much of the Midwest was cropped and drained, the landscape was dotted with marshes and water-filled surface depressions that provided habitat for migratory waterfowl and other wildlife. Drainage water management systems can be used to recreate these landscape features. Marshes and ephemeral wetlands can be established in uncropped areas and in water-filled surface depressions in crop areas during the non-cropping season. The main benefits from drainage water management are related to the ability of the practice to reduce nitrate loads from tile-drained fields. Several studies in the Midwest and elsewhere report tile load reductions of 18 to 80%. These figures might not represent total nitrate load reduction, as very few studies account for all the transport pathways. Some studies have demonstrated limited yield increases from the practice. However, such benefits are not as significant or as consistent as the water quality benefits. In paired comparisons with conventional drainage, there has not been any significant reduction in nitrate concentrations from drainage water management systems. The dominant mechanism for nitrate load reduction from drainage water management systems is the reduction of tile outflow. Nitrate concentrations in water leaving the field through other pathways are lower than concentrations in tile water. In some instances, drainage water management has also reduced phosphorus loading from tile outflow. DrainMod was used to simulate a drainage water management system with 4-foot deep tiles in Drummer silty clay loam. 30 years of hourly precipitation and daily temperature data from Urbana, Illinois were used in the simulation. The field was in a corn-soybean rotation and drain spacing was varied from 40 to 120 feet. For each spacing, infiltration and flow rate decreased, and runoff and evapotranspiration increased on the drainage water management. With drainage water management, the tile outlet level can be raised during the growing season, potentially storing water in the soil profile. The volume stored is dependent on rainfall patterns and outlet elevation and is highly variable. There is therefore the potential for yield increases, particularly if stored water is available at the time of reproductive growth when plants are most sensitive to water stress. NRCS develops and implements conservation plans to protect, conserve, and/or enhance natural resources. These plans address one or more resource concerns. Drainage water management has an impact on a number of these resource concerns. Drainage water management is most effective when implemented as part of an overall nutrient management plan. Such plans are developed to budget and supply nutrients for plant production, properly utilize manure or organic byproducts as a plant nutrient source, minimize agricultural non-point source pollution of surface and groundwater resources, protect air quality by reducing nutrient and/or particulate emissions to the atmosphere, and maintain or improve the physical, chemical, and biological condition of soil. The benefit of a comprehensive plan is more than the sum of the component parts. Drainage water management may be combined with other water management practices to enhance nutrient reduction or crop yield. Practices are often combined to address weaknesses inherent in each component practice. When implemented in combination with bioreactors or saturated buffers, the standard control structure developed for drainage water management may be modified for dual use. Dual use structures are less expensive than the individual structures for each practice. When drainage water management is implemented in combination with subsurface irrigation, water is added to the upstream section of the control structure to maintain set water table elevations in the soil profile. The combination results in consistent yield improvements. It is best suited for new systems since the drain depth and spacing required for subsurface irrigation and conventional drainage are not the same. When drainage water management is implemented upstream of a constructed wetland, the outlet level may be set lower than it would be set if the practice were implemented on its own. The lower setting increases the potential soil water storage, thereby reducing runoff and the likelihood of flooding or erosion. Details of constructed wetlands are presented in the Related Conservation Drainage Practices module. When drainage water management is implemented in combination with a cover crop, there is potential to store more water in the soil profile, which might result in a more established cover crop and more vigorous crop growth. Care must be taken to not set the outlet level too high so as not to drown out the cover crop. When drainage water management is implemented upstream of a bioreactor, the outlet level may be set lower than it would be set if the practice were implemented on its own, thereby reducing runoff and the likelihood of flooding or erosion. Details of bioreactors are presented in the Related Conservation and Drainage Practices module. When drainage water management is implemented upstream of a saturated buffer, the outlet level may be set lower than it would be set if the practice were implemented on its own. The lower setting increases the potential soil water storage, thereby reducing runoff and the likelihood of flooding or erosion. Details of saturated buffers are presented in the Related Conservation Drainage Practices module. General criteria have been used to determine suitable tracts in the Midwest for implemented drainage water management. While these criteria provide a broad outline of the extent of the applicability of the practice, there are overriding site-specific factors that should be considered. Is there an existing systematic drainage system or plans to install a systematic drainage system? If there is an existing clay tile system, are there existing maps and what is its current state of integrity? Will the implementation of the practice adversely affect neighboring fields? How convenient will it be to maintain the system? Will the system make it inconvenient to cultivate or harvest the field? The NRCS has developed maps of cropland in the Midwest suitable for drainage water management. The criteria used to define suitability include major soil components, land slope, hydric soil classification, and parcel contiguity. Land suitability data have been compiled for each county in the Midwest. These data are based on the generalized criteria mentioned above. However, when it comes to determining if a particular site is suitable, the most important factor is the ability to maintain an elevated water table without adversely affecting neighboring fields. The most important factor in determining soil suitability is the ability to sustain an elevated water table. Most soils with this ability are classified as being hydric, but there are exceptions. Soils classified as being hydric typically require drainage and for the most part are suitable for drainage water management. In undrained cropland, these soils have free water on the soil surface or water within 18 inches of the soil surface for 5 or more days in the growing season. Soils occur in associations, and it's unlikely that a field or mapping unit will only contain one soil. All of the soils in a field may not be suitable for drainage water management. A parcel meets the components criterion if the majority of the soils are suitable. Drainage water management practice standards define the treatment area as the area within 2 feet of the control elevation for that structure. Flatter fields are preferable as fewer structures will be needed per unit treatment area. In addition, the use of multiple structures inconvenience agrotechnical operations. Fields or sections of a field with an average slope of 0.5% or less are more likely to be suitable for the implementation of drainage water management. On steeper slopes, the effective treated area can be increased by using multiple structures. Multiple structures are most suited for fields in which the laterals are parallel or near parallel with the contour lines. To minimize water leakage from the edges of drainage water management systems, fields or sections of fields are considered more suitable if they are larger than 15 acres. The edge factor of a field may be defined as the ratio of the perimeter of the field to the perimeter of a square of equal area. The closer the edge factor is to unity, the more suitable the field is for drainage water management. This experiment consisted of a pair of drainage systems in the same field, one under free drainage and the other under drainage water management. Both systems were instrumented to measure flow and water table levels. When the outlet level was raised in the drainage water management system, water leaked over into the free drainage system, and vice versa when the outlet level was lowered.